In this video, we will solve a two-dimensional elastic collision problem. In this problem, an atomic nucleus of mass m traveling with speed v collides elastically with the target particle of mass 2m initially at rest and is scattered at 90 degrees. Part A, at what angle does the target particle move after the collision? So what happens here is we have a nucleus, a particle. So a nucleus is moving with a velocity of v and mass m. And another particle which is at rest, let's call it P, okay? Because this N means nucleus and P means that's a particle. With a mass 2m, it's at rest. And then this particle nucleus collides with this particle at rest, and then after collision, nucleus, it said, is scattered at 90 degrees. It goes vertically upward, okay, with respect to the horizon, 90 degrees. And well, particle P must also move towards down, because if nucleus is going up, this P should go towards down, but we don't know at what angle. So let's say here is the horizon, and this, let's say it's moving towards down because the other one up, this must be down, but we don't know at what angle with respect to the horizon. We don't know. We are going to find this angle, okay? So since this collision is elastic, in elastic collision, we have two conditions. Number one, the momentum is conserved. Sigma pi before collision is equal to sigma pf final after collision. So this is the sum of the momentum of the whole system before and after, the whole system, if the system is made up of some particles. And the other condition is the energy is conserved, okay, because it's elastic. So initial energy is equal to final energy before collision is equal to after collision. Okay, so since this collision, two particles move in different directions, this is a two-dimensional collision. In two-dimensional collision, we need to consider and study the law of conservation of momentum in two dimensions. First, x dimension, and the next one is y dimension. Okay, so now we need to study the law of conservation of momentum in two dimensions. So first of all, x dimension, the mass of nucleus m times velocity of nucleus v, because the velocity was towards x-axis, okay, plus the mass of the particle 2m times the velocity, which was 0, is equal to, so this is before collision, and the part after collision, m, the mass of nucleus times, since it goes directly towards up, it does not have any component to the x-axis because the angle is 90 degrees, so it's purely vertical, plus 2m, the mass of the particle times the velocity of particle after collision, which we let's show it by v prom p, and then cosine alpha. So we multiply it by cosine alpha because we need to find the projection of this velocity v prom p on the horizon, on the x-axis. That's why we need to multiply it by cosine alpha. So after simplifying this equation, we will get to this part: velocity v of the nucleus is equal to 2 times v prom p, the velocity of particle after collision, times cosine alpha. So this is one of the findings that we have found. This is, let's say, it's equation number 1. And in y dimension, let's move on to the y dimension. In y dimension, we say, okay, the mass of nucleus times the velocity of nucleus, which was purely horizontal, so here we have 0, plus 2m, the mass of particle, times the velocity of particle, which was 0, is equal to the mass of nucleus, which is m, times the velocity of nucleus, which is vertically upward. Okay, so we do not need to find any projection because it is purely vertical, times v, let's say n prom, it means after collision, v of the nucleus after collision, okay, plus 2m, which is the mass of particle, times v p prom, which is the velocity of the particle after collision, let's call it that, times we want to find the projection of this velocity towards negative y-axis because it's towards down. We need to multiply it by sine alpha, but remember, since it's towards down, we need to take into account the negative sign, okay, the negative sign of this. Or we can say we do not consider the negative, we just say this alpha is not alpha, is 2 pi minus alpha, okay, it's 2 pi minus alpha, so therefore it will be sine 2 pi minus alpha, or let's say beta, which is different from alpha. Therefore again it will be negative sine alpha. Okay, so again negative here appears, whether we just take it into account or we take the correct value of this angle into account. Again, automatically this negative and positive will pop up, will appear. So therefore, let's say times negative sine alpha. Okay, so then after simplifying it, this is 0 0, these two. Okay, so after simplifying, we will get v prom n, it means the velocity of nucleus after collision, is equal to 2 vp prom, the velocity of particle after collision, times sine alpha. So see, we have got another equation. Let's call it equation number 2, equation number 1, equation number 2. And here, the first one, we got the velocity of the nucleus before collision, and here the velocity of nucleus after collision. We found it based on the velocity of the particle after collision, the relationship between these two velocities. So okay, all right, so this is done. We are done with the law of conservation of momentum. Now let's move on to the law of conservation of energy and see what we can get from there, what equation we can get. Okay, so the second law of conservation of energy, we will get to energy of this system before collision is equal to energy of system after collision. Okay, so let me write it here. Before collision, we have got nucleus, which was moving, and P, which was at rest. Nucleus, the mass m, particle, the mass 2m. Okay, so therefore it will be a half of mv, the velocity was v, to the power of 2 plus, since the velocity of the second particle was 0, so therefore 0, because it was at rest, is equal to a half of m, mass of nucleus, times its velocity after collision, v nucleus after collision, squared, plus a half of the mass of particle, which is 2m, okay, and the velocity of the particle after collision, vp prime squared. Right, so this is the law of conservation of energy, and then after simplifying it, we will get to this part, v to the power of 2, the velocity of the nucleus before collision is equal to velocity of nucleus after collision squared, plus 2 times velocity of particle after collision squared. So this is the equation that we can get from this law of conservation of energy. Now let's say this is the third equation. So look carefully at the findings we have found. Let me write these two others here, equation number 1 and 2, and let's see how we can simplify these three equations to get to the point where we can find the alpha. So equation number 1 was, because we want to put them together next together to see what we can do. Velocity of nucleus is equal to 2 times velocity of particles after collision times cosine alpha. This is equation number 1. And equation number 2, which was velocity of nucleus after collision is equal to 2 times velocity of particle after collision times sine alpha. Okay, so this is another equation that we got, number 1 and number 2. So now we have got these three findings. We need to simplify from there. We need to get somewhere from here. Well, looking carefully at these three equations, we see the equation obtained from the law of conservation of energy. They are all squared and they have the power of 2. And look carefully at these two equations, we will see they have sine and cosine. So let's raise both sides of these two equations to the power of 2 and see where we can get to. So let's say v to the power of 2 is equal to 4 times equation number 1. 4 times velocity of the particle after collision to the power of 2 cosine to the power of 2 alpha. Okay, so this is the equation number 1. I raise it to the power of 2. And the other one, which is velocity of nucleus to the power of 2, is equal to 4 times velocity of particle after collision to the power of 2 times sine 2 alpha. So now these two equations, if we look carefully at, we will see cosine squared alpha and sine squared alpha. It reminds us of this famous well-known trigonometry equation, which is sine alpha to the power of 2 plus cosine alpha to the power of 2 is equal to 1. So this reminds of us this trigonometry equation. Okay, so therefore we can say, let's add up these two equations together. Let's add them together. If we add them up, these two equations, we will get v to the power of 2 plus v nucleus prom to the power of 2 is equal to 4 v particle after collision vp prom cosine alpha to the power of 2 plus 4 times v particles prom to the power of 2 or squared sine squared alpha. Okay, now we factorize from 4 vp prom to the power of 2. So I missed this power of 2. We need to put on the power of 2. We can factorize, and then we will see here will be cosine alpha to the power of 2 and sine alpha, which is 1. Okay, so this is a new equation that we obtain here, vn prom to the power of 2. So this is the new equation that we have got here. Okay, all right, now we were just trying to simplify these two equations. We did not get involved with the equation number 3, which was obtained from the law of conservation of energy. So and now let's put these two equations next to each other and see what we can do with these two equations. So let me write this equation of law of conservation of energy down next to this. V2 or V squared is equal to when V nucleus prom to the power of 2 plus 2 the velocity of the particle squared. Okay, so this is another equation. So look carefully at these two equations. We will see that, well, we can actually simplify these two equations, because if we add them up, these two equations together, we will get a different and a new equation. So okay, now let me just rearrange this equation again. V squared minus, if I move this v and prom square to the left side of the equation, will be minus v and prom squared is equal to 2vp prom squared, which is the velocity of particle after collision. So now see these two equations. Okay, here we go. We can add them up. So let's add this one with this equation. I will write it right below here. V to the power of 2 or v squared plus v and prom squared is equal to 4 times vp prom squared. Okay, all right. So if we add them up, this v nucleus prom, they will cancel out each other, and then we will get 2v2, okay, is equal to 6 vp prom squared. This is what we found. All right, now we are getting to a better conclusion. We can find the vp prom, the velocity of particle after collision, based on the velocity of nucleus. So we can say, therefore, vp prom squared will be equal to 2v squared over 6. All right, so also we can just simplify it. This is 1 and this is 3. They can be simplified. Therefore, we take the square roots from both sides of this equation. Vp prom is equal to v divided by square root of 3. Okay, so this is the value of v p prime based on the velocity of the nucleus before collision. So now we have not got the alpha yet. We have not got any alpha during our simplifying, but let's get back to the findings that we already got here, obtained the equations. So we got equation number 1, 2. Okay, looking at equation number 1, we will see we have found the velocity of particle after collision based on the velocity of nucleus before collision, and there is a cosine alpha there, so maybe we need to just substitute the value of Vp prime into this equation and see if we can simplify it further and if we can finally find the alpha. All right, so therefore we can say, here I will write the equation down. V velocity of nucleus before collision is equal to 2 velocity of particle after collision times cosine alpha. This equation was obtained after the analysis of the law of conservation of momentum in x dimension. So this is the first equation that we found. Okay, this is the equation number 1. All right, so let me substitute the value of Vp prime here, and I will get V is equal to 2 times, instead of Vp prime, I will write V over square root of 3 cosine alpha. Okay, right, so now we are getting closer and closer. We can simplify these velocities together. They will cancel out, and then it will be, and then cosine alpha will be equal to square root of 3 over 2, right? And we know what angle the cosine of that angle is square root of 3 over 2, which that angle is 30 degrees. Okay, so we found the angle. This is part A. We already got the answer for part A. Okay, and part B, let's read part B now. Part B says, what are the final speeds of the two particles? So the speed of the two particles, we already found one, the velocity of particle after collision. So let me again rewrite it here down. So let me see, V, this is part B. So let me just write the velocity of particle after collision is equal to velocity of the nucleus divided by square root of 3. So this is one, but we don't have the velocity of the nucleus after collision. We don't have that, so we will get back to the second equation that we obtained at the beginning of this analysis, which is the relationship between the velocity of nucleus after collision and the velocity of particle after collision. So I will write it here, which was the velocity of nucleus after collision is equal to 2 times velocity of particle times sine alpha. Okay, so now here again I will substitute the Vp prime by the value that we have got. Okay, and then it will be Vn prime, or the velocity of nucleus after collision, is equal to 2 times V divided by square root 3 times alpha is 30 degree and sine alpha is 1 over 2, right? And then so we will simplify, and then we will get V over square root of 3. So this is the value of the velocity of nucleus after collision. We are done. Well, these two values are the same. The velocity of nucleus after collision, the magnitude, and the magnitude of the velocity of particle after collision. The magnitudes both are the same. Okay. Now part C says what fraction of the initial kinetic energy is transferred to the target particle. So that means we need to calculate the kinetic energy of the particle after collision and kinetic energy of the nucleus before collision, and then divide the particle, that of particle to that of nucleus. So let's say kinetic energy of particle. So after collision, okay, this will be equal to a half of mass is what? 2m, and the velocity of the particle after collision is what? Here we go. V over square root of 3 squared, okay, which this will be equal to m times v squared divided by 3. Okay, and now the kinetic energy of nucleus before collision, the kinetic energy of nucleus before collision. It will be equal to a half of m, and the velocity of this particle nucleus was v squared. Okay, so then since we need to have the fraction of the initial kinetic energy of the system to the target particle, we need to just simply divide kinetic energy of particle by the kinetic energy of nucleus, and then it will be equal to m v squared over 3 divided by a half of m v squared. And after simplifying, so we can simplify it, then it will be equal to 2 over 3. So 2/3 of the kinetic energy was transferred to the target particle, which was that particle with a mass of 2m.